is an aerospace engineer from Cryotech Instrument. Sorry. Yeah. So Martin is an aerospace engineer from Cryotech Instruments. He have worked in satellite projects like PWSat, Bright PL1, Bright PL2, SAT AIS PL, YES2, and the Solar Orbiter. He is the author of the concept HyperSat satellite platform, and now he is an engineer in HyperSat team. So, welcome, Martin. General I think the microphone is not working.
To creating this presentation here, thunderstorm, etc. Okay, welcome again, everybody. It's glad to meet you, everybody here. And today I would like to talk about the new satellite standard. I would like that you should thinking about this, that maybe this is something where the CubeSat project can go in the future. Where is the position? Position of the HyperSat is for people who use the CubeSats and they thinking that CubeSats are too small for them, so they want to something bigger, maybe not as big like this SSTL 150 platform, but maybe for low cost. And we are talking about the satellite, which the mass of this is something like up to 60 kilograms, is scalable, power is something 50 watts, 50 megabits communication system, ILCS, everything on board, and everything will be on open hardware and software licenses. This platform is designed by two companies. First is my own company, this Cryotech Instruments. It probably is the biggest space company in Poland. And the other is the Space Research Center, is the scientific institute where I work. Before I worked in the Cryotech from something like 7 years. And probably is the biggest scientific institute in Poland who producing the components who fly in space around the Earth or around the Mars and other projects. And this platform has everything. There's the communication system, power system, onboard computer, OSCS, and mission control software. And for people who just want to join to this platform, there's something which we are called PBA. This is prototype bus adapter. This is just the very simple board for connect to this platform some own instrument or something like that. And for people who just, like you have the board in the CubeSat standard, we will have on the board something like the 1U CubeSat, which will be connected to our bus, which we are called the HyperSat data network. This is like the structure looks. This is just in the middle, so because the structure can be scalable, something from one HyperSat unit. This is the 35 to 10 centimeters, and this 10 centimeters can grow up to 60 centimeters. If you look inside, there's the rack for the Space VPX boards. Here you see the example of it. And if something is too big for this standard, there's the shelf when we just mount other elements like the for example batteries, reaction wheels, or for example this place is just for this one new CubeSat adapter. This satellite will be not use the pivot like the CubeSat because pivot are heavy. We use something that we call marmal clamp, and we have the team who just designed this specially for us. This marmal clamp will be compatible with several rocket systems, like here the name ISPA. And the base ground of the satellite, base of our research, maybe your instruments, because we just read several papers about different instruments to just check what people need from the platform. Because you know, the very important thing that if you are thinking about satellite, the reason why we are going to the space, it's not the satellite, it's the instrument. We are flying to space because we want to send instruments. And the platform is everything just for control this instrument, powering, communication, then, etc., etc., etc. And I try to thinking how to measure the complication of these instruments, or how it's expensive, these instruments. And probably for me, the best measurement is just the mass of these instruments. So this platform is designed for the mass up to 50 kilograms. And I want to show you a few slides which show you how these instruments in this class looks like. This first class, the first slide, it shows you that the size of these instruments. On this here, you see if you're thinking about the instruments like the cubic, this is one of the edge of the cubic size. And if somebody look correctly, you see this approximation is wrong. It should be rather linear than something like that. So maximal size for our satellite is something like 25 kilograms. So theoretically, we can just bring bigger instrument that we design. About the power. If you're looking for the power for the instruments, the power for the biggest satellites, the biggest instruments, is something like 30, 40, 50 watts per instrument. And if you just put the solar cells on CubeSat like this, or the satellite like this is not enough. This is not enough. You need more solar cells. So we just creating. This is the simulation from, I don't know, 2 weeks ago. We just add additional solar cells just for powering this system. And I think that this is very small missions to fly without additional solar cells. Next subject is the RF link. RF link, we want to design this RF link especially for the satellite, thinking about the 50 megabits for communication when the satellite can set direction of the antenna to ground station in omnidirectional, something like megabits. But we have the problem, we find the team who just can design for us. And finally, we probably use the Syrinx modules just for the CubeSat like this, and the parameter you see here. About storage, storage is completely differential systems. So we plan just put something average. So it means there's some 16 gigabytes per gigabytes for our satellite. If somebody needs more, we can just add some additional card for this. IOC is accuracy. IOC accuracy doesn't change from the size of the satellite or this instrument. For CubeSat, there is very small, and then it's something average. It depends on the missions. Our goal is something here, so we want to pass minimals for all instruments which are found. If we are talking about the bus, normally on the CubeSat we use something like the CAN or serial or something like that. We want to use something faster, so we plan to use the something what we call space wire, but this is expensive. This is expensive because it uses a lot of power. So finally, we just probably mix them. This is with space wire with connection with the CAN. It will be, as I told you, that this is the Space VPX standard. On board we have two this space wire connections. You can just watch this model. This is our prototype of this board. All of this board like this will be connected on the background by this connector board. And you can just put your payload and other modules in different places in this rack, just for changing the configuration. For people who are not happy with using this some complicated system, we have something what we call a network interface card adapter. This is specially for this is designed just how to connect this complicated interface to something simpler, like the serial UART LVDS. And at the end, we just do some of the measurement, how much power this system uses. If we are checking this, if we use the space wire, we need for the bus something like 3 watts, so it's a little too big. If you want to just, if you needn't so fast communication, you can use CAN interface, then you save something like half of the power in this situation. And here, this is the board which I show you. This board just I sent 2 days ago with the Lufthansa in the vibration test, in the flight. Please careful about this because we lost some of the screw there. But on this board, we're just testing how much power this system uses. Here we have this element for this IP core. Okay, I just finished. And there's some of the DC to DC converters, which we are just testing how efficiency it works. And when I just push my engineer, show me the results, how it works, he showed me the screen like this. So it's margin, it's alive. It generates some of the data. We see that one interface is getting something like half of the watts. So it's something what we expect. And here we see some of the efficiency of our DC-DC converters. It's something about 70 to 80%. And this is what I want to show you. This is probably the first mission which we are planned to use this platform. This will be the astronomical mission with all of this component. And this is how the satellite looks. And if you remember the previous presentation, this is the 3D printed too. This is not really satellite, but it works. So finally, this is very important. It can be something what the CubeSat change to bigger mission. So this platform will be open. We plan to publish any documentation in 2 years from now. This platform will be focused on just cheap components, etc. This platform will focus on fast send to space. We are thinking about something like 6 months from design to send to space. This platform promises faster communication, faster bus, etc., etc., and it will be open just for you. And if somebody just wants to join to this team or this platform, or just want to watch the documentation, just call to me, and I send you. Thank you very much.
Thank you. So, questions? This guy.
Hi. I was curious about the deployment mechanism or the deployment ring that you were contemplating. You said that you were thinking about building a proprietary mechanism for deployment of the HyperSat.
Okay.
I'm just curious if there's what drove you to that, or if there's anything standard that you might use or that you had to pass up.
There's the standard Marman clamps, which you just buy. They are not cheap. So this is why we are thinking about build by own. We have the team who just working on this. And we want to creating something like that. Half of them will be designed to different rockets, and rest, it will be compatible with all of the satellites. So if you build your satellite, it will be just easy to find the rocket for you, because rockets will have the other part of this of these instruments.
Thank you.
Over there. So with such a bigger satellite, you usually want to go further into space. So what you do about radiation hardening when using these commercial components?
It's based on the idea from the CubeSat. We want to send to space just commercial components. The best is if this component has some of the history in the space, and this history shows that it works. It's important, not just that it's broken in space. But still, I believe it's much more important to fast sending something to space and show that it's working than just build very long-term mission. It means that when we are designing this platform, we are thinking about the startup. You know, that the startup just getting the money from the venture capitals. You have $10 million, show me your demonstrator in 1 year. And this demonstrator can work 1 week, show me that it works. And they haven't the platform just for do it, because it's, the bigger platforms are much more expensive. Smaller platforms like CubeSat are too small for them. Building own platform, you need something like 2, maybe 3 years for this. And this is a very, very good solution. Just connect this element. Maybe you pay a little more for this simple solution, but you can show in 1 year for your investors working satellite in the space.
Okay, thank you. All right. This is Marcin. He asked a lot of questions. You can take revenge.
Okay.
So it's a matter of iterating, right? You said you want to send it to space because you learn so much when you send to space also. So I always look at this time, this is more like a comment, look at this time while you're a grandpa or double grandpa and you have your grandkids saying, replying to you when you tell them, yeah, I was doing CubeSats and small sats, and they would tell you, yeah, grandpa, we know. We sent one last Sunday on the free launch of SpaceY, as usual. We bought the parts at Whole Foods, so that's for the California guys. So you never know what's going to happen in the future. Everything's going to be easier for the next generation. So
I think that I think that generally we have the changing in the generation of the people about thinking about small satellite. If you ask people in the ESA 10 years ago that maybe you should build so small satellite, they just looking for you just like the child.
yeah.
The small satellite, there is no money there. So why we should build small satellite? But now the market pressing is so high that ESA just thinking about the small satellite because this is the solution.
All right, yeah.
This is the solution, and this is why these people who are here just will be building this satellite.
Yeah, so this is the last talk of the workshop, and then we'll have work groups this afternoon. So big thank you, Marcin.
Thank you very much.